going to talk about eventually about gravitational waves and LIGO-India, and I'm very glad to be here. But initially, in order to talk about gravitational waves, I have to talk about black holes, and I will start at a very elementary level, so that I hope that some of you who know a lot about these things don't get bored at the beginning. Stay with me, and I'll eventually get there. So let us try to introduce the concept of a black hole in a very classical sense, in familiar terms, for people who have encountered the concept of gravity in school. In Newtonian gravity, in school, we are taught Newton described gravity in terms of a force. Gravity is a force where between any two massive objects of mass m1 and m2, and so the force acts along the line that is joining these two masses, and is inversely proportional to the square of the distance. This is something we learn in school, and this is something Newton proposed many centuries ago. A consequence of that is that if you want to get away from this force, you need to attain a velocity which is called the escape velocity, and that is the equation for it is given here. It is proportional to the mass of the object you're trying to get away from, the square root of that, and inversely proportional to the radius of the object that you're getting away, the distance from its mass, right? And so that means that you can actually define a black hole in this kind of situation as well, even though in order to describe a black hole, you really need to employ what I'm going to talk about a little later, which is Einstein's description of gravity. What you can say is that a black hole is a quantity, is an entity which is such that to get away from it, you have to exceed for an escape velocity, the velocity of light. And of course, we know that the velocity of light is the maximum you can attain, and so nothing can escape from a black hole. So the concept of a black hole, even qualitatively, if not quantitatively, can be attained from this particular description. So how can you make something into a black hole such that the escape velocity from it can be as high as the speed of light? And that is an interesting idea. What you can do is, for example, you can keep the radius the same and increase the mass of an object, and because that 2gm over r quantity gets bigger and bigger as the mass increases. But the other thing you can do is that if you keep the mass the same, is to decrease the radius of the object. If you make it smaller and smaller and smaller, then m over r becomes higher and higher, and eventually you can attain a velocity that is very high and can exceed the speed of light. Now this, if you do that, I mean, so it just tells you that anything can turn into a black hole. Even you and I can turn into a black hole, but somebody needs to squeeze us into a very small radius, and you have to find a physical process that can do that. If you look at what that means in terms of the Earth's velocity of escape is about 11 kilometers per second, 43,000 kilometers per hour. So if you think you can drive a car fast enough to break free of gravity on the Earth, that car doesn't exist. In fact, such a spacecraft even doesn't exist. We actually, when we take a rocket away from the Earth, we still, at least in the Indian context, we can't have a rocket that can attain that velocity directly. There are ways of taking the rocket higher and higher away from the Earth, so that the escape velocity is low enough so that we can attain a velocity to escape. So it is very, very difficult to do that. For the sun, it is even higher, 600 kilometers per second, and this is why the Earth is trapped with the sun. It is not escaping from it. You can also see how small something has to be in order for the escape velocity to exceed the speed of light. For the Earth's mass, it has to be very small, as you can see, very tiny, of the order of a centimeter or so, in a millimeter, and then for the sun's mass, it is something like 3 kilometers. So you have to find something that squeezes a sun into a few kilometers across, and this is how you can make a black hole. And so you can see that if it's to do with you and me, then we have to squeeze ourselves to something that's even smaller to become a black hole. So this is known as the Schwarzschild radius, which is given by this very simple equation, and you can plug in something and see it's just proportional to m. So you can look at something that is 10 to the power 9 times the mass of the sun. The radius of that black hole would just become 10 to the power 9 times that. Okay, so that's something to keep in mind. Now, of course, Newton's idea of gravity doesn't really hold very much close to, for speeds very much close to the speed of light, or for masses that are very massive. And so we have to go to a different idea. And because Newton came up with this idea of gravity being a force that acts between two objects, Einstein pointed out at the beginning of the 20th century that that is not a very general concept, because what happens is some things are traveling very fast, close to the speed of light. How do these objects know which direction they're being pulled, for example, and things like that? So Einstein's description for this became something that was very, very different, very local. And Einstein came up with an idea that you can describe gravity in the most general sense by saying it is not really a force, but it is a consequence of the mass of an object distorting space-time around it. And so space, in Einstein's formulation, space and time together, they are related, and it actually exists. It has a form, and it itself can be bent. Whereas in Newton's theory, between the planets and between the stars, there is nothing. It's vacuum. Whereas Einstein is saying that the universe has a fabric, and that fabric is space-time. And when you put a mass somewhere, it distorts space-time, and as a result, things get trapped in that distorted space-time, and that gives rise to gravity. And so, in this particular formulation, gravity is not a force, but things move along this distorted space-time in natural trajectories, in straight lines, as it were, which is the shortest distance between 2 points, and so sometimes that can be a curved trajectory. And also in Einstein's formulation, you can see that even light can bend, because in Newton's formulation, light doesn't have mass, so it couldn't have been affected by gravity. In Einstein's formulation, light follows this curved space-time, and so it can bend along space-time. Waves can go along space. So this is the idea. The idea is that if space-time is given by this kind of green grid, it's not really green and it's not a grid, but it gives you an idea of what Einstein is saying. Then due to the sun, locally the space-time is curved, and the Earth is trapped in that trough, as it were, and going around the sun in a trajectory that is defined by this curved space-time, and that gives you a definition or a way of thinking about gravity. But so Einstein formulated this in 1915. Actually, in 1916, he said he predicted gravitational waves, but I'll come to that in a moment. But this formulation helped us understand, how to describe quantitatively the curvature of space-time. Carl Schwarzschild, within a few months of it, solved Einstein's equations in the case of a massive object, and how space-time will be curved around a massive object, and which led to the formulation of the size of the black hole. So, which is why we call Schwarzschild, call it by Schwarzschild's name. We call it the Schwarzschild radius. And of course, Schwarzschild did this while he was a soldier in the First World War on the Russian front. He was doing his mathematics in a little notebook while during the war, and he actually died in 1916 before his work was published. But he'd written his solution in a small postcard, sent it to Einstein, and Einstein published it in Schwarzschild's name. But we know his lasting legacy is that during the war, he actually was solving Einstein's equations, one of the first people to find solutions for it around massive objects. So that gave us the formulation of how to calculate these in spherically symmetric cases, how to calculate these distorted spacetimes. But the person who really told us how to make a star into a black hole was Subramanian Chandrasekhar, who about a decade later started thinking in terms of quantum mechanics, which was coming out as a new subject at that time, combining it with this concept of a curved spacetime, and came up with scenarios of how stars will evolve, how stars will finish their life, and what happens after a star stops producing energy and things like that. And he realized that stars, when stars stop producing energy, there's nothing to stop them from collapsing, and they can collapse to very small objects even, and there are quantum mechanical forces that are going to stop them from collapsing on the way, and some of the stars will turn into white dwarfs, and some of the stars will turn into neutron stars, and some of them will turn into black holes. So this whole thing about squeezing a star into something that is a few kilometers across is a process that can occur naturally for stars, because when a star is a star producing energy, its shape and size is sustained by the energy it produces. So this is a wonderful way of finding out how naturally you can produce black holes in the universe. And that also led to this idea that if you really have this a black hole, which is has masses of stars, or maybe hundreds and thousands or even millions of stars in a particular small part of space given by the Schwarzschild radius, then the distortion it causes on the fabric of space-time is so huge that it can create this, you can see a distortion like a tunnel that goes down a very deep well, and so from that to come out is very difficult, and even light cannot escape from it. And so you can pictorially see in this kind of a distortion of space-time what a black hole would look like, and it would have an event horizon, and something that falls into it will never be able to climb out of that event horizon. So this is how I want you to think about black holes. So we know that there are these black holes that are created from the evolution of stars, as I just said, which are maybe up to 100 times the mass of our sun, because the most massive star we've seen in our galaxy so far is about 100 times the mass of our sun. So if we have to produce black holes from them, they have to be smaller in mass, because throughout the lifetime, stars lose a lot of mass, and then finally, when they explode and the inner core turns into a compact object like a black hole or a neutron star, it is much smaller in mass than. So how can we produce more massive black holes? Because what happens is that in the center of each galaxy in the universe, we see supermassive black holes. Black holes, there is one per galaxy in all galaxies, and in all major galaxies, that is not dwarf galaxies, not satellite galaxies, but major galaxies. And in the middle, we see supermassive black holes that are a few million to a few billion times the mass of the sun. And those cannot come from single stars. And so their formation is a mystery. And so people have proposed that maybe these small black holes merge to form these big black holes in the centers of galaxies. But then we should be seeing black holes that are a few hundred times, few thousand times, few 10,000 times the mass of the sun, which we don't see. In fact, we didn't see until very recently. The first discovery of a black hole that is greater than 100 times the mass of the sun was announced only 2 weeks ago, and through one of the LIGO detections, which I'll talk about in a moment. So this is what happens when stars die. As I said, if a star is about 1.4 times the mass of the sun, it becomes a white dwarf, and that's going to happen to our sun because it's naturally less than 1.4 times the mass of the sun. it turns into a neutron star if it's between that and about 3 or 4 times the mass of the sun. And when it explodes, this is a picture of the Crab Nebula, which is an explosion of a star that happened about 1,000 years ago in 1054 AD. And we have seen that it's left behind a neutron star in the middle, which spins very fast, and it's a pulsar. If it's about 3 or 4 times the mass of the sun, the compact object in the center collapses to become a black hole. So this is a consequence of what Chandrasekhar showed you. The reason we cannot see a black hole is this. This is a picture of a black hole. Nothing comes out of it. We see everything in the universe because of light or any form of radiation that comes from it, but a black hole does not emit any radiation. And so you cannot see a black hole. And this is why for a long time, people thought that black holes can never be detected. In fact, in Cambridge, I did my first course on black holes from Stephen Hawking in the 1980s. And Stephen Hawking at that time was betting everyone that black holes will never be detected. From the 70s, he placed some very high profile bets with some famous scientists. But of course, very soon we realized that we can actually see black holes. We can only see black holes through the effects of the black hole, because it's such an extreme object, on the surrounding space-time. And to understand that, we'll have to look at how a black hole can be perceived, if not directly seen. We'll have to look at how we perceive things from the universe. We look at, we see things in the universe through electromagnetic waves, either through the light that is emitted from it, and you can see the visible light comes from right at the center of this electromagnetic spectrum in a very small range, and this we call visible because our eyes are sensitive to it, but we can actually detect now any form of electromagnetic radiation all across. You can look at smaller wavelengths or higher frequencies, and you go into ultraviolet, X-rays, gamma rays, and then in the longer wavelengths, low energies, you can see microwaves and radio waves, etc. And all of that gives you information about celestial objects. Black holes, of course, being such an extreme object, will cause quite a lot of high energy phenomena to happen around them. And so what we are looking at is looking at ultraviolet and X-rays emitted from, if you're looking in the electromagnetic waves. But the problem is that the atmosphere is opaque to most forms. Actually, it's a coincidence that the kind of light that our eyes are sensitive to, that is also where the atmosphere is transparent. So this is why we see the stars. If our eyes were sensitive to X-rays or ultraviolet, we would not have known there's a universe out there. There's a radio window also when the atmosphere lets through radio waves, but you're looking at X-rays, gamma rays, and ultraviolet rays. You have to go above the atmosphere. And this is why, for example, one of the ways we have found black holes is to go and look at the universe from space. Here is the Chandra X-Ray Observatory that I was part of when it was being built in the 90s, and it was launched in 1999 by NASA. And it is an X-ray telescope which was built to find black holes. And it was named after Chandrasekhar, of course. And it is in this amazing orbit, which takes it all the way about 122,000 kilometers away from Earth, because it has to stay away from these radiation belts surrounding the Earth. And it is shut down half of the orbit when it comes very close to the Earth. And it can observe only in its 64-hour orbit, only half of the time. It's got these special mirrors that can form images from X-rays, because as you know, if you put a mirror, normal mirror in front of an X-ray, it will go right through. X-rays go right through us. But if you have X-rays incident on a surface at a very small angle, then it can be reflected off the surface. That is because the wavelength of X-rays is very similar to the interatomic spacing in solids, which is nanometers. But if you actually are incident at a very, very small angle, that interatomic spacing becomes smaller. the effective spacing becomes smaller, and it can still reflect off X-rays. And so that is why the Chandra X-ray telescope is so long. What it does is these mirrors gather these X-rays and form exquisite images. The images have the same resolution as the Hubble Space Telescope in the optical. This is the only observatory in X-rays that does it. So what are we observing? What we observe with these X-rays are black holes that exist in binary systems. Now, in most stars in the galaxy are in binary systems. The stars don't like to live alone. They live with other stars, so they're in twos. In fact, our sun is an exception. And that's because Jupiter did not become a star. But most stars actually are in binary systems. So say there are two stars and one star is bigger than the other. Bigger stars, more massive stars evolve faster. And so what happens is that as they evolve, one of those stars will go supernova and say it forms a black hole. So here you are, it's formed a black hole in the middle. And then this black hole is orbiting then another star, which is a normal star that was small, but that will also continue to evolve. And at a later stage, it will evolve. As it evolves, it becomes larger. And as it becomes larger, its outer layers have less gravity pulling it towards the center. And so it will reach a phase where this black hole, the effect of this black hole, the pull of the black hole on the outer layers will be larger than the pull of the own star on its outer layers. And as a result, matter will start falling onto the black hole from its binary companion. And it will pull matter onto itself. And the matter will not fall straight into a black hole because it has some angular momentum. So it will move around the black hole and form a disk. And that disk will get very, very hot because of the gravitational potential energy of the black hole. It will become 10 to the power 7 degrees hot. And at 10 to the power 7 degrees, things emit X-ray. So here is an artist's impression of how in an X-ray binary, what happens is that the matter falling into a black hole, as you can see, the black hole itself looks like that. We've seen a picture of that recently, as you know, through the Event Horizon telescope. It's something which looks exactly like a black hole, but surrounding, you have this accretion disk that is going to glow in X-rays, and as you can see, it will emit X-rays, and this you can see. And here is a picture, for example, of a galaxy, a nearby galaxy. I just wanted to show you an example. This is from my own work with the Chandra X-ray telescope. Here's a galaxy, and what you're seeing here is a picture which is taken with a normal optical telescope. This is what Centaurus A looks like. This is not an X-ray telescope. This is a normal telescope taking a picture. So these are real stars in that galaxy. Centaurus A has been caused by two galaxies colliding with each other and forming a very nice round object. You can see everything in this particular picture is a few thousand degrees hot. That is why it produces optical light. Our sun is 6,000 degrees, as you know. And if stars are between about 2,000 to 3,000 degrees to about 8,000 to 10,000 degrees hot, they mostly emit their black body radiation in the optical range, and you can see them like this. So I can tell you that almost everything in this picture is emitting optical radiation, and so they are a few thousand degrees hot. We took the Chandra X-ray telescope after it was launched and pointed it at Centaurus A, this nearby galaxy, for about 1 million seconds, and we got a picture like this on the same scale. And here, everything that you see in this picture is 10 to the power 7 degrees hot, 10 to the power 3 degrees hot, 10 to the power 7 degrees hot, at least 10 million degrees hot. And you can see that there are all these little blobs in the galaxy, which you won't see here. But these are the X-ray binaries, and many of them have black holes in them, right? I had a student who did his whole PhD on analyzing every single of these X-ray binaries, and found that some of them, that one there, these actually have black holes in them. The others have neutron stars in them. So this is one way of finding black holes, the X-rays that are emitted by the black hole pulling matter from their binary companion. You also see that the center of this galaxy here, right in the middle, which you can't see here, has a black hole that is 10 to the power 9 times the mass of the sun. And what happens in such a black hole is that it draws in a lot of gas that is left behind between the stars and falls into this black hole. And it falls at a rate that the black hole cannot really take in. So this black hole then emits this this gas at very high temperatures and at very high speeds. And this is what you see here. That central big blob is a supermassive black hole in the middle of the galaxy that is emitting a jet of material that was falling into it but could not get into it. Now, this is plasma that is maybe 10 to the power 7, 10 to the 8 degrees hot, and it is traveling at 99% of the speed of light across the entire galaxy. And that, so in this particular picture, you see both the stellar mass black holes and the supermassive black holes, all one supermassive black hole in the galaxy all together. So here you are. So till a few years ago, the way we gathered information about black holes of both the stellar mass kind and the supermassive kind was through X-rays. And you can see that you can actually directly see them, well, not directly, but indirectly see them through the effect they have on their surroundings. There are other ways of finding black holes, for example, through their dynamical methods, etc., which I'm not talking about today. So we know that we can find these millions of little black holes that can exist in a galaxy, and also one big black hole in the center of the galaxy. So what about these black holes in the middle? And for a long time, through X-ray observations, people have claimed that there are 100,000 solar mass black holes that have been found, but nobody's really been able to find things like that without a caveat in them or unambiguously find them. So in India, we have this project that I'm going to talk about, which actually looks at finding black holes that are more massive than these black holes that you saw through another method, not through electromagnetic waves at all, but through gravitational waves. And these mega science projects in India, one of them is LIGO-India. And I'm going to now talk about why we are planning to build this in India, and what the motivation behind it is. You know that gravitational waves were discovered for the first time. What I showed you before were electromagnetic waves. They come like light and X-rays and gamma rays and ultraviolet. They come from disturbances, electromagnetic disturbances of electromagnetic fields, but not all objects might have electromagnetic fields. But we know all objects have gravitation, and gravitational waves are also like electromagnetic waves, but they come from gravitational disturbances of the fabric of space-time. And they were, this was predicted by Einstein when he formulated this theory of general relativity. And that is because if space-time is a fabric, then anything that moves in space-time in a certain manner will cause ripples or vibrations of this fabric of space-time, and they will propagate. They may propagate in the form of gravitational wave. The first one instance, and of course in 1916 Einstein wrote another paper saying that they will never be found because they will be very tiny disturbances in the fabric of space-time, and they're so tiny that they will never be detected. Now, they were detected, of course, the first time exactly 100 years after Einstein published his theory in 2015, and instantly led to a Nobel Prize for the people who had built the LIGO Observatory. And in the discovery paper, there were about 40 authors from Indian institutions. There were 1,000 authors of the whole paper, and Indians played a very important role in developing the whole subject of how to detect gravitational waves and how to even model what kind of gravitational waves will come out of merging compact objects like neutron stars or black holes. Einstein's theory, as I said, not only predict that light will bend as they go around this bent space-time, the fact that if you have compact objects moving around each other, they will stir space-time such that gravitational waves might propagate. So many of you would have seen something like this before. And this, for example, is an animation of two black holes and their distortion in space-time. And look at the times here. We're talking of a fraction of a second in which happens where two black holes going around each other will lose energy due to gravitational waves being emitted and come close to each other. And as they come closer and closer and closer, you can see in the bottom panel, the frequency of the gravitational wave is increasing. That is a hallmark of gravitational waves, that as the things come closer and closer together, the frequency goes up. And this has just been slowed down, the movie, just to show what happens right when the two black holes come very close together. You can see that the distortion in space-time is actually merged, and it becomes one black hole. And as a result, it forms one single black hole. Now, what happens is that as this gravitational wave goes through space, the distortion of space-time happens such that there is extension of the space-time along in one direction and a contraction in the other direction, and that is also a sign of the gravitational wave. And this is what is then used by us in this LIGO configuration, where one takes an interferometer, which is like a Michelson interferometer that a lot of people here would be familiar with if they have worked in a physics lab, in which a beam splitter splits through a laser beam into two parts. And what happens is, if this works, is that the laser beam comes and is combined together. Actually, it can reflect between them like this about 200 times, and then is joined together. And if they are traveling along identical paths, and in the case of LIGO, they're 4-kilometer paths, then they will exactly cancel each other. In here, there is nothing coming out of this of the cancelled beam, as it were. But what happens is then when a gravitational wave passes through the system, these two parallel perpendicular paths get distorted in different ways, and as a result, one of these will contract and one of them will expand, and the balance between the two beams is going to be off balance, and then you detect some of the light coming through. And this is how, in a nutshell, the LIGO detector works, is that it relies on the fact that you have the two perpendicular directions, and the way gravitational wave is propagated through space-time, it will contract one direction and extend the perpendicular direction. And as a result, light will travel along slightly different paths. So it turns out that the displacement of that you are measuring, the amplitude of the gravitational wave, is of the order of 10 to the power minus 21 in terms of a strain, which is the distortion of space in delta L divided by the scale on which it is measured. So, for example, if your gravitational wave detector is kilometers across, then the displacement will be 10 to the power minus 18. And just to see how small it is, you can see that human hair is about 10 to the power minus 4 meters. A wavelength of light is about a micron, 10 to the minus 6. And the diameter of an atom is 10 to the minus 10 meters. A nuclear diameter is 10 to the minus 15 meters. And so this is 1,000 times smaller than the nucleus diameter of a nucleus, which is why Einstein said, no, there is no way humans can ever measure this, right? Because it is so small compared to the smallest particles. And yet we did. This was the first time in 2015, almost 5 years ago, actually 5 years and a week ago. It was detected by these two detectors, which look like this. As you can see, it's a Michelson interferometer, 4-kilometer arms. This is from Hanford, which is in Washington State, and Livingston's observatory is in Louisiana State, 3,000 kilometers across, and they have identical setups in these two places. These are evacuated tubes, which are have a nanotor vacuum inside, with lasers bouncing around, suspended optics, and I'll show you some pictures. And both of them detected the first detection that happened on the 14th of September 2015. You can see the characteristic, and this is actual detection now. I showed you a simulation before. Characteristic detection of the gravitational wave at Hanford and in Livingston. And if here in the bottom panel, what one is plotting is frequency as a function of time. And you can see the frequency. This is called a chirp because the frequency goes up. And this happens within about a fifth of a second, 1/5 of a second. This was the first detection that that was found. And from the nature, the details of this detection, we can figure out what it is. We found out that this is because within 1/5 of a second, this is due to the merger of two black holes, which are roughly about 30 solar masses each. In fact, it was 39, 26, something like that, and so times the mass of the sun. And this is a picture that one of our students produced to show what the Schwarzschild radii of these black holes would look like. If you take the Schwarzschild radius formula, the event horizon of these black holes would be as large as small states in India. Has nothing to do with black holes in India, by the way. This is just to show where the scale of these black holes. So these are much bigger black holes than the ones that we were discovering with the X-ray, which were very much in the mass range of 3, 4, 5 solar masses. These are this was the first one that was discovered, and so we found that two roughly 30 solar mass black holes merged to form something that is a 60 solar mass black hole into 62 solar mass black holes. And if you took the 39 and 45, the two, no, not 39, 45, but whatever the two were, you add the two together, it was 65 times the mass of the sun. So the final black hole is 62 times the mass of the sun. So there was a deficit of 3 solar masses, and that can be explained in terms of that mass being transferred into energy equals mc squared, and the whole being radiated as gravitational waves. So I'm going to now, since then, till the LIGO Observatory was shut down a few months ago, just because of the pandemic, we have had about 70 or so detections that have been announced. There have been many other detections that are still being worked on, which will be announced slowly. I will highlight a couple of them, which have been very, very interesting out of these gravitational wave detections. One of them was the detection of 2 neutron stars. In fact, in the planning stage of LIGO, people thought that these were the things we would find first before the black holes, but the black holes surprised us. Now, this GW1708, you can see that it was discovered in August 2017, on the 17th of August. And this was special because this is the only case so far in which we have seen an electromagnetic wave counterpart of the gravitational wave source at the same time. Normally what happens is when gravitational waves are detected, because gravitational wave observatories are not very directional, that the direction uncertainty is so high that electromagnetic wave telescopes, which are optical telescopes or something, cannot really find them very quickly, and there will be effects in the electromagnetic regime. But in this particular case, we were very lucky because it was associated with a burst of gamma rays, and a gamma ray telescope caught it. In fact, in the optical, we found that it was near this particular galaxy, and that was the event. And it faded over a period of days. And this led to a very interesting campaign of follow-up, which if you listen to Varun Bhalerao's talk, he will talk about it, I'm sure. And a very interesting follow-up in all across the electromagnetic spectrum of gamma rays, X-rays, optical and radio. And this told us a lot about what happens when compact objects merge to form gravitational waves. Incidentally, this is also very interesting because almost all the gold that we see on Earth would have been formed in mergers of neutron stars. And so if you are a user of gold in the form of any jewelry that you wear, you are actually now holding something that was formed in one of these mergers from which we just detected gravitational waves. I want to also talk about the most recent announcement, which caused a lot of sensation. It was something that was discovered last year, but only announced a couple of weeks ago. And GW 1905 is a very interesting object in which two black holes of 85 times the mass of the sun and 66 times the mass of the sun had merged together to form 142 times the mass of the sun remnant. This is the first time we found something that is larger than a 100 solar mass black hole. And this is the first time as a direct evidence that this intermediate mass black holes that we've been thinking about or debating about has been found, and it provides a kind of link between the supermassive black holes on one end and the small black holes. Shows directly that actually by hierarchically merging small black holes that are formed from stars, you can form bigger and bigger and bigger black holes. This is, as you can see, the two black holes that merged themselves could have come from smaller mergers like this. You can see the first one that was detected is this one, which have these two forming together a black hole of this size, but then this and this, like here, could have merged to form something like that. And that gives us a whole new era of physics to look forward to. So here's a summary of the kinds of black holes that have been found by the different methods I've been talking about. The purple ones are the ones that have been found through X-rays, and they are in the range of 5 to 10 times the mass of the sun. The most massive ones are about 15, 16 times the mass of the sun. Whereas the blue ones are in each gravitational wave event, if they are black hole mergers. Now we have discovered events where there's one black hole and one neutron star merged to form a black hole. Two neutron stars have merged to form a black hole. But these are systems in which there are two black holes that have merged to form a black hole. And each system we see three black holes, right? Three masses. And they're all plotted here. On the y-axis, you can see the mass. And this one, as you know, is 140 times the mass of the sun. So you can see that through gravitational waves, we're looking at a different class of objects that we've never seen before, and we can see only in this gravitational waves. It's interesting why we haven't seen these things in X-rays yet, but of course, these have to be in X-rays to see them. They have to be in binary systems, accreting matter, and maybe these massive black holes in their current form are not in binary systems where they can accrete matter from others. They obviously are the ones that we have detected. They are two black holes in a binary system, not in a binary system with another star. And so the ones we have detected here are actually merging black holes, or merging neutron stars. To detect them, it is very, very important for us to understand how the detector works. And so I'll look at what LIGO, the challenges for LIGO are. If you look at the frequencies at which these things are detected, they're about 10 hertz, 1 hertz, that kind of thing. And this is a measure in the y-axis of kind of sensitivity of the black hole. I'm sorry, my power is going off and on. So in the illumination, you will see some variation here. But my slides should be all right. So there, in the sensitivity, this shows how different kinds of noise can hide the signal from gravitational wave. Now, you're talking of something that is extremely tiny, the signal, and it's normally in astronomy, we have the signal above the noise. Here, the signal is many, many orders of magnitude below the noise. The noise comes from many things. It comes from normal seismic noise. The Earth is vibrating, and also, people going around and cars going around, all kinds of things. There is pause-on noise, shot noise. Then what happens is that you have the mirrors, and everything is suspended from from fibers, and these things themselves have noise that is thermal noise, and they vibrate. The pressure of the radiation when the laser hits the mirror causes radiation pressure, that has its noise. Then there are lots of other kinds of noise that are very, very high, and you have to be above it. And so you have to bring these noise down, but also each kind of noise has its own signal, and so one learns to recognize what kind of noise you are detecting in a particular frequency, and what a signal looks like compared to them, right? And so these instruments are very, very sensitive, and you can see, for example, if you go into the LIGO papers, you will see plots like this all the time, and you can see the different kinds of noise have different dependence on frequency, a different color here, and the actual detectors have a noise profile like that, and you have to actually have a detection that is above this profile, or even if it's below this profile, then we have to find that signal within that noise. And so that's the main challenge, and so we have to find a place where we can build this detector and the noise, and we bring the noise levels down. So here is what the current status is now. The two LIGO detectors that detected the first gravitational wave has now been joined by another detector built in a very different way. It's a 3 kilometer by 3 kilometer array called Virgo in Italy by the European consortium. There was one in Germany called Geo 600 for a long time, 600 meter long, which didn't detect anything, but actually built all the technology for it. Then Kagra in Japan is starting, that's also a 3 kilometer array underground. It's starting to operate. It started just before the pandemic, closed down everything, but he operated through the pandemic, hasn't detected anything yet. And then we have LIGO-India, which will be built hopefully 2025. Now, of course, these timelines are slipping right in the middle of India. And what happens is that when LIGO-India comes, because the baseline is so long, it will help us locate the source to very small areas in the sky. Currently, for example, if you see the gray area here, that corresponds to the localization of the very first detection that happened. And with LIGO-India, that if LIGO-India were there at that time and detected the same source five years ago, we would have to localize the source in a small area like that, a few degrees, which is a few times the size of the full moon. As you know, the full moon is a half a degree across, and so it is easy for electromagnetic telescopes to go and find these things. So we're going to build LIGO-India, and it's going to be right in the middle of Maharashtra in a district called Hingoli, near the town of Nanded. And what we have done now is signed an MOU with NSF in the US that the third LIGO detector, in fact, they built 3 sets of detectors when LIGO was first commissioned. 2 of them were installed in these 2 places. The third set was not installed, and they are collaborating with us, so they will send the detector and the lasers, and we're going to build the infrastructure here to install them. And so this is going to be the third LIGO, which will be in India, and it will look like that. As you can see, this is actually the blueprint that DCSEM, the civil engineering firm, part of DAE, which will build it, has made. And you can see the 4 kilometer arms and the central station in which the laser will come together is being now designed. And the 4 institutes that are going to take part and build this is IUCAA, of course. We are looking after the science that goes behind LIGO, and we will look after the operation once it is built. And the Institute of Plasma Research in Gandhinagar is going to build the vacuum system. The RRCAT in Indore is going to build the lasers and the suspension system, etc. I'm going to be another 5 minutes, and I'll wrap up a description of LIGO. This is what it looks like now. The place where LIGO is going to be built. This is where the 2 arms are going to come together, and so that has been marked. And as you can see, the land is very undulating, so all has to be leveled. There's a huge amount of construction work that will start once the money is fully approved. It is now not yet approved, and everything has been in the last few months delayed a bit. Lots of work going on in that region, with holes being dug to do geotechnical surveys. We are doing seismic surveys there, and some work is going on. It's very, very exciting. The actual these are pictures of different parts of the beam tubes in the existing LIGO detectors in observatories in the US, and you can see intricate, very intricate kinds of equipment that are going to be built here, and these are all going to be assembled and built. For example, the optics is going to be suspended in 4 stages, such that it's completely isolated from the surroundings in terms of vibrations. As you know, a pendulum is isolated from the motion of its from where it is suspended, but if you do many stages, then it completely isolates. These are the mirrors themselves are like this, and they're isolated from the vibrations and of the building. So even if you shake the building, the mirrors don't move. And so these things will have to be built here, and such things are being built. The vacuum system, etc., is being built by Institute of Plasma Research, and they have built such vacuum systems before for the ITER project, for example, where it has to go down to nanotor, as I said, very, very high vacuum. Right now, we have a fantastic team who are going around the site, interacting with the general public there and the kids in schools, and trying to educate them about astronomy and LIGO and whatever is. As you can see, school children have really engaged in this, and this talk that we are organizing today is being organized by the same group in collaboration with IISc, and so they are a part of the education and public outreach group in LIGO, and we have very good social media presence. Go and look us up on Facebook and Twitter to see what we are doing. I leave this you with this list of books that you can go read up on when what I talked about. If you want to look at Einstein's life and how Einstein conceived this whole idea of gravity, is a very good biography of Einstein. Kip Thorne, who got the Nobel Prize for being one of the people who built LIGO, has this fantastic book called Black Holes and Time Warps. And if you're interested in time travel and wormholes and things like that, look at Richard Gott's book, which is a fantastic book. I'm going to stop here and hand you back over to the organizers. Thank you.
Thank you for a very interesting and enthralling talk. Let us move on to the next section, which is the Q&A session. So we have a very enthusiastic response with many questions which we have got. I'll start. The first question is, how can we find the source of gravitational wave once we have a detection? How do we localize the source?
We don't. So what happens is, right now, as I said, if you, for example, think of a gravitational wave detector as a microphone. If you have one microphone, you don't know where the sound is coming from, right? So if you have a single gravitational wave detector detecting a gravitational wave, you wouldn't know where the thing came from. Because there are two, in the case of LIGO 1 and LIGO 2, Hanford and Livingston, the first one, then you could have some idea of where this came from. There's a 7 millisecond delay between the two in the detection. So that is why you saw that little strip in the sky, and you knew that the source had to be in that direction. But that strip itself is a few hundred square degrees. The sky is 40,000 square degrees. So, so a few hundred square degrees. And so the source can be anywhere there. Right now, the detections are being made by 3 detectors, the third being in LIGO, in Virgo in Italy. So the baseline is longer, and with 3 detectors, you can bring that much, much smaller. And so it's now a few tens of square degrees. Now, with LIGO-India, it's going to become even smaller. And so if all 4 detectors or all 3 detectors detect a particular object. From that, you can triangulate and find the direction of the gravitational wave. That's the idea. That's how you can do it.
Our next question is from Gurkirat Singh. Since 10 power minus 21 is a very precise measurement, even small errors due to local sound waves must be removed. What are the ways such errors are minimized at the LIGO observatories?
So not just sound waves, everything. For example, there are very tiny disturbances that can cause what is known as noise. And the gravitational wave science is entirely a science of trying to minimize noise and also to identify noise, right? So for example, why is the tube evacuated to 10 to the power 9 torr? And that is because if, for example, there was any gas in that gas molecules themselves, the laser going between mirrors would impinge on them, and they would cause some kind of a thermal noise because they have motion in there. Okay, so they would introduce some noise. They can scatter the laser light as well, and so that will cause another kind of noise. Then the vibration of the mirrors themselves that are suspended, those suspensions have some vibrations. Now the mirrors themselves have coatings on which the laser comes and hits, and that coating itself has a thermal noise. So it distorts the coating as the laser comes and hits within the spot, and that also has some kind of a vibration. And so we have to find, for example, the coatings of these mirrors that will have very low noise. So all this innovation has been done to isolate the suspended optics from the surroundings, as well as to minimize the noise in each of these levels. I can give you an example of a very esoteric kind of noise. It's called Newtonian noise, which is, if you have the mirror that is suspended and the earth vibrates under it due to normal seismic activity. Earth is always vibrating slightly, but we're talking of 10 to the minus 18 meters, right? So the earth vibrates slightly, and so the gravitational force between the earth and the mirror changes very slightly because the earth is vibrating and the shape of the earth is changing. That is a very important noise called Newtonian noise. So you can see we have to pay attention to all these little things. In India, when we put this gravitational wave detector, it is going to detect those waves that bounce against the coast, east coast and west coast. Every single wave will cause a vibration of the Indian, the Deccan Plateau, and that will be detected. This is an amazing precision at which one needs to find. So what happens is that one of the ways the gravitational wave is detected is a process called template matching, in which we know what the gravitational wave signal looks like, and so even if the noise is much higher than the signal, we can find the signal because we know what it looks like, right? But the noise, of course, has to be much smaller. So there are, we can give you hundreds of hours of talks on how to detect, how to bring down the noise at these various levels. I'm just, mentioning some of the features.
Yeah. The next question is slightly related to what you just said. What are the reasons to choose the proposed site at Hingoli in Maharashtra? Was it due to less seismic disturbance, or is it because it's located in central India?
Oh, there are many. It was the whole story. Someday needs to be written. A whole story of finding the site was very, very interesting. When the team that set aside, I was not part of that team. This was done quite a while ago. Set aside to find in India. One of the first things, one of the constraints that was given to us, that it has to be at least about 10 to 15 kilometers away from any railway line, right? Try to find a place like that in India. Very difficult. India has the densest railway network anywhere in the world. And then it has to be not very near a major city, because there's a lot of human activity causes a lot of vibrations. But it also has to be near, reasonably near an airport or a major city. Otherwise, where will the people live and how will things get there? So, and then the seismic activity is a very important thing. the quality of the soil or the rock on which it is placed is a very important thing. So the team started from looking at ISRO's Cartosat maps of India at high resolution, because at that resolution, even Google Maps were not available to us. So ISRO gave us its highly classified maps of India at that resolution. In fact, a bunch of undergraduates, principally from IISc Kolkata, did a very good job of very good job of writing little programs to look for places where you could have this kind of topography, as well as this kind of isolation from cities and railway lines, etc. And finally found several candidates, and we did seismic surveys there. And it turned out this place is seismically extremely good. In fact, the American builders who had built LIGO came and looked at our site in Hingoli and found that it was about 10 times quieter seismically than any of the American sites, because, as you know, the American continent is very seismically active. The Deccan Plateau is one of the most stable places on the Earth. And we have a place where, if we can do a good job, we can build a LIGO detector that's better than the ones in the US. Because the basic noise structure is very little, and the nearest town is about 10 kilometers away, small town, and the nearest big city is about 100 kilometers away.
Okay. So the next question is, what accounts for the sudden decrease in the waveform of the gravitational wave after it reaches its peak in the choke waveform? Also, why is there a slight oscillation at the end after that?
It is all in the detail of how black holes merge and what happens in the merger. And so this is in the physics of the black holes in the merger, as well as the effect it has on space-time itself. When the merging process is going on, the two black holes are coming closer and closer together. And so the effect on the space-time is changing constantly. And that is why you see a lot of features in the waveform. But after it merges, actually what happens is that the merged black hole oscillates for a little while and then settles down into, so there's a ringing part, and then it settles down into a black hole that is formed, which is a single black hole. And now when a black hole is there, it is just moving as a single black hole, not as two different objects. And so it is not as complicated so it depends on, the lumpiness of the system, as it were. The different moments that you can think about, the quadrupole moment, the octupole moment, and stuff like that of the distribution of mass determines the nature of the gravitational wave. And so if, for example, you have two things merging, three things merging, they'll be very complicated, and so the waveform will be complicated. But if it's one object moving as a single object, and it's not oscillating or not spinning, then it will have a different waveform. So this is why before and after merger, the gravitational waves are different. The waveform is different.
Yeah. So the next question is from Kiran Mehta. Do you envisage a future where it will be possible to build gravitational wave observatories in space to increase the baseline, so to increase accuracy?
Yes, of course. I mean, this is, if you looked at the wavelength or the frequency at which we are observing now, the frequency is about a hertz or 10 hertz, 100 hertz, something like that. And these are tuned to merging stars and maybe explosive events, some of these supernovae, etc. But there are all these other gravitational wave sources that can be detected. For example, gravitational waves from the Big Bang itself, and all these other things, and they actually are detected at various other frequencies. And so those frequencies can only be determined if the size of the observatory is much bigger. So smaller frequencies. Now, in this kind of setup, you can't really make it much larger than 4 kilometers because of the curvature of the Earth. You can't make it much larger because you'll have to have lasers bouncing between mirrors, And the curvature of the Earth means that the mirrors have to be much larger. Otherwise, you can't make it much larger than 4 kilometers. People are trying to make 10-kilometer size, the next generation earthbound things underground, so that these can be compensated. If you want to make it much larger and go to a very different frequency, then you have to go into space. And so LISA, for example, if you look up LISA, LISA was conceived long time ago, and the US had considered building a set of 3 satellites bouncing around in space, where the laser would go between these 3 satellites, millions of kilometers apart, not 3 kilometers, 4 kilometers, but 3 million kilometers apart. And the laser light would bounce between them in mirrors that are in. And so a test was done, LISA Pathfinder, where this was tested. But then NASA canceled this mission, and so they decided they couldn't fund it. So that was cancelled. Now it has been taken up by ESA, European Space Agency, and they are planning to build a smaller version of space-bound gravitational wave observatory, which is the planned mission is in 2037 or something like that. And they're trying to think about building this. I think ISRO has very much an interest in this. And at some point, it could be that India will get involved in this. And I'm hoping that we will in the space-bound gravitational wave observatory as well.
That is a very interesting answer. Our next question is from Anand. So he's asking, how does a gravitational wave get affected when it passes through various objects which it will encounter on its way from the black hole merger to Earth? Does this not affect the information which we can gain about the original system?
Yeah, it can. I mean, just in the same way as light is affected as it comes from a distant object to us. We know that electromagnetic waves, light, as it comes from a distant source to the Earth, they pass by massive objects and they bend. And as a result, the light beams give rise to multiple images of the same source, and also distorted images. I didn't talk about gravitational lensing today, but that's a wonderful subject. Now, gravitational waves can also be gravitationally lensed because they are coming also through the universe, and it passes by massive objects, and those massive objects locally distort space-time. And so the gravitational waves are distorted. And as a result, you will experience gravitational lensing of gravitational waves. There are papers being written on it right now. Very interesting subject. And but you know, I mean, looking at electromagnetic waves, our vision of the universe through light, we can see most of the things that we want to see. We can compensate for the gravitational distortion it might have, and even find some information about the masses distribution of matter in the universe from it. Maybe someday through gravitational wave observations, we can do the same. Okay, let's go for the next question.
Yeah. The next question is from undergrad. He is saying, what are the ways in which an undergrad student can contribute to the LIGO-India program?
Okay, so this is a very interesting question. I mean, of course, LIGO-India is being built in India, not for the benefit of a few scientists, but for the whole country. And for the whole country, I mean, everybody who studies in any university in India, teaches in any university in India, does research, everybody should take part in this project in various ways. And as we build it, we require more and more people to get engaged in the various activities. And when it is built, of course, to use LIGO-India to do the science. Now, while it is being built, it is a massive engineering project, as you can see. This is not just an engineering project in which a contract is being given to a company and it's fully designed. There is a lot of developmental work that needs to be done. In particular, I showed you some of the pictures of the suspended optics and the vibration-free environment, the vacuum systems, and the various designs that need to be done in producing these things. Already, we have engaged a very large number of institutions, many IITs, BITs, BITS campuses, as well as ICERs and various other universities are involved in particularly departments of optoelectronics, departments of mechanical engineering, departments of civil engineering, departments of physics, all kinds of and electrical engineering and control engineering, of course. The electronics and control side of it, and so all of them are involved in developing various bits of it. Now, interestingly, from now till the time it will be built, 2025 or so, LIGO is going to evolve, and now we are part of the LIGO project. So we are part of the evolution of the LIGO system. So whatever happens in the US or in Europe for the Virgo project, we have to be part of it. And so that research needs to be done by people. So what can a PhD student do? What can a MSc student do? And what can an undergraduate do? They have, in order to do that, there are various levels at which they can engage with the project. As we set up the system here in the various institutions in LIGO, you will find that LIGO related projects will be available. Already they are available at the various institutions that are taking part. You can write to us through our social media channels, and we can tell you where the nearest institution is to you, where you can actually take part in such a thing. You can get involved in the research projects as part of your undergraduate work or as your postgraduate work. And some of the institutions have started giving courses on LIGO related science. This will increase exponentially in the next few years. You will find that as part of your undergraduate and postgraduate course, you will have LIGO related courses to be given as well. So please keep engaged in them. If you can do a little research project along with at any of these places, write to us and we will put you in touch with the people who are near you. And then worldwide, there is LIGO related projects going on at the various institutions that are involved in LIGO. There are more than 100 institutions that take part in the LIGO project worldwide. And you can work in any of these institutions to gain experience. And in the end, of course, when LIGO-India is built and starts working in 2026 or so, you will find that the whole world will come here to work with LIGO. And of course, if you're an undergraduate now, you'll be a fully qualified astronomer by then to make use of LIGO. So this is the time to start.
I'll just take one last question. Can we detect gravitational waves formed due to the Big Bang? And can gravitational wave astronomy help us to understand the origin of the universe?
Yes. In principle, yes. Because we, as you know, when we look in electromagnetic waves, the farthest we can see is the cosmic microwave background. And that is the background which is left behind from the energy that was created in the Big Bang. Because before that, in the first 100,000 years of the universe, the photons that were part of the universe were interacting with matter in such a close manner. The plasma itself was such that it was not transparent, it is opaque. So photons have not escaped from the early part of the universe coming to us now. So when we look back in time, we look further and further away, we're looking back in time, we can only see up to a certain part and not beyond that, and that is the cosmic microwave background, which is at a time when the universe was about 1,000th of its current age. But in principle, we can see gravitational waves much further than that, all the way to the Big Bang. Because when the Big Bang happened, and we don't know what happened at the Big Bang, why did the Big Bang happen, what happened at the time of the Big Bang, we know that that's our T equals 0, and a lot of energy was created at that time. But it would have certainly created at that time the space-time that we see, and that space-time would have a signature of events very close to the Big Bang, if not the Big Bang itself. And those things would have happened at a time when the universe was very, very small. So the frequency of this would have been very different from the gravitational waves we detect now. And so in principle, it can give us a lot of information. I'm saying in principle because even the theory hasn't been worked out yet in detail. This is something that's happening now, and this is why a very interesting is this whole idea of bringing quantum mechanics and gravitation together, and to try and understand the basic kind of physics where at this very tiny universe at the beginning, quantum mechanics would have been very, very important, and we don't yet have a quantum definition, a quantum formulation of gravity called quantum gravity. And so so that is why we don't know the theoretical background of what we will see if we can detect gravitational waves from that time. So gravitational waves can help us understand the quantum nature of gravity. It can help us understand the nature of gravity as it was being created, as the universe was being created. So in principle, it's a very, very exciting field. And that's where theory and observations have to converge at some point. So in this whole field, kind of, it is exciting because we are at a stage where, say, atomic physics was in the year 1900, when the electron is just being discovered, and we can see that the atom has different parts in it, right? And suddenly, atomic physics, nuclear physics became wonderful subjects. Quantum mechanics was invented, and between 1900 and 1920, 1930, when the neutron was discovered, all this happened. That experiments started telling theoreticians what to expect, and the experimenters created new experiment, and then understood what's inside the atom. In gravitational wave physics, this is happening now. We are discovering things, and we are also, the discoveries are telling us what to do in the next round of experiments. And then theoreticians are coming together and trying to explain all that. So it's a very, very exciting time to be a gravitational wave astronomer.
Thank you.